So check it out. We're defining a new function. To be honest, the moment we defined vectors, we went to the new world of vector fields and vector calculus. So we can now define a function of vectors called vector function. In general, if you define any new tool, you can make a function out of it. You want to make a function of your hair and the color of it? Yeah, let's make a function of that. Function is a tool that helps us to work with stuff we just defined. So a vector valued function, or just a vector function, that's a short way to say it, everyone know it, is a function r of t. It's not a vector, it's a function. R of t, no bar over there, no error. Domain is your input, is a set of real numbers, and range, those are outputs, are vectors. That is a pretty cool idea. R is, we can split R into its components. Input times I, input times j, and input times k. F, g, and h are called component functions. They're functions of R, component of the function. And the range of R is a curve in real numbers, 2D or 3D or whatever it is. So in American education, they like to show this idea of the toolbox. This is like a machine, like a robot machine. The machine job, that's a function. Function is a tool, it's a machine. The job of the machine to swallow, wow, that is very beautiful, but not necessary. How did they even create that? Okay, good. Swallow something and then spit out something. Swallow input, right? Input, spit out output. Input is domain, so it takes the domain and spit out range. Well, range is accumulation of all the things that will be counted as output. So it's pretty cool. It takes in a number, a real number. So it takes in number, does something with it, and that's what this machine represents. Does something with that number, and takes out a vector. Can you imagine that? How cool is that? So I give you 5, and you give me a vector 1, 3, minus 17. I give you 17, and you give me a vector 0, 0, 1. What is the correlation? How did it happen? How did we jump from one point into a 3-dimensional object as a vector? And the vector is what? What is the two qualities of the vector? Magnitude and direction. Direction, magnitude, exactly. So how come we, from a number 0.7, we jumped into error, which has a beginning, the direction, and the size? That is pretty cool. And the arrow defines things. We just learned it. We can define things. When t is moving, the position vector traces the space curve. So let me show you some cool things. Find the vector equation of the circle centered at 2, 3 and radius 4. Those are classical beginning level things. Again, let's work with equations of circles, but this time everything is a vector equation. So you first draw it. Why it's so slow today? You draw it first. Here's a circle centered at 2, 3, radius 4. Radius 4. So what we're doing here, we want to trace the circle. Again, tracing it is pointing at it. Last time we learned it in vector calculus to sketch anything. There's a pointing vector, for example, like this. And this vector is keep pointing and moving through the object. So that's why it says tracing. Maybe I should stop. This is what I'm talking about. We're tracing a line. Last time we learned how to trace the line. Yeah, maybe I should close stuff. Yeah, it's totally super slow. We're tracing the line by pointing at it. So let's trace a circle by pointing at it as well. Here it is. That means creating those equations. If they are asked to given in the parametric form, we have x equals and y equals. Let's do that. Parametric equations. Parametric equations are x depends on t, y depends on t, equals. Starting point and direction. Starting point and direction. Well, R here is, see in blue. Let me highlight it. This is my R. Is going to be a vector function. So it is a vector. I think I accidentally said it's not a vector. R is a vector that has x and y as inputs. R is x and y, but now it's a vector. X depends on t, y depends on t. Can you guess? We have always the same notation, starting point plus slope times the function. So we have starting point is kind of obvious. What's the starting point for x? 2. That's the beginning. We're going to start at 2. And for y, 3. And then we're going to have the size, the slope. And the slope in this case is not obvious. It's not a line. But we're basically saying how far we can go, how far we can trace. We can trace 4 units far. That's because of the radius. And then we're using material from the end of the Calculus 2 class. 4 cosine theta, 4 sine theta. We call it t in this case. It doesn't matter. But t is an angle. Sine t. Sine. C, sine t. Yes. This is good. So this is how we're first going to be attempting writing down the equations. Yeah.
Can you just briefly go back to the thing where you said as r varies, the head of the position vector, it's right above the...
Yeah. Thank you.
When t varies.
As when t is running, varies, right? When t is changing, the head of the position vector r traces the space curve. Space curve is the curve we want to describe. In this case, it's a circle. So that's what I'm trying to show you. Let me move a little bit. That to describe the circle, I'm using r. I'm pointing at it somewhere at the very beginning. When t is changing, I'm tracing it. So we don't describe the circle anymore as all the numbers are away from the center with the same distance. Now we're actually pointing in it and tracing it. Yes?
Does the initial point of the vector always start at the origin, or do we sometimes start at the center of the circle?
We try to start with origin. That's a more general case. In some cases, the question is good. Does the pointing vector, this vector we're using, always starts with a 0? Sometimes not, but it's easier to move it there. And because the parallel vectors can be moved around, it's nice to move it back to the 0. And originally, this is the way we're defining it, but you should be open-minded. In general, everything can get more complicated. So now, t is also important. T in this case is not infinite. It's a time or angle, whatever that thing is. In this case, it's an angle from 0 to 2 pi, like so. So here's my parametric equation. So very interesting that you don't have to write this down, but whatever we just wrote, well, actually you should write it down in the differentiation. That's called a vector function. R is a vector function. It's a function that has x and y as inputs. X and y are numbers. It's cosine of t, say pi over 2, times 4 plus 2. That's a number. X and y are numbers that depend on the location at the time t or angle t. So when t is changing, r is moving. But then when r is moving, these inputs become 2 plus 4 cosine t and 3 plus 4 sine t. And that describes a circle. When t is starting at 0 and finish at 2 pi, and actually it's keep going as a circle, but at least one circle rotation is from 0 to 2 pi. So this function describes a circle. Very interesting. This is an example of a vector function, where for every time t, in this case it's an angle, we give you a vector r. So all the vectors will be different, right? So when t is 0, let's see if I'm showing this. Oh no. When t is 0, we can calculate this number and this number. Y will be 3, because sine of 0 is 0. So y will be 3, and then cos, and then 2. So 2, 3. We start from here. We're pointing it here. Then t is growing. Oh, it's 4, see? So t is growing, and then the trace is keep moving. And at some point, it will finish pointing and everything. Again, we're not moving on the circle. That's what I think I'm making it more confusing showing this. There's always a pointing vector, like so. And at a different time of t, it's a different pointing vector, just like in this cool animation. I think this is the best representation I found to explain. We keep pointing at every moment of time. And at some point, we pointed at everything we need, and that everything became a circle. That is pretty cool. I don't need that. Next, how about cosine? So this is, I want you to guess what this is. Sketch the curve, cosine t, sine t, and t. What the heck is that? What do you think? I kind of want to ask several questions. If you can guess, use your imagination, open your mind. X, y, and t. So we have x. X behaves like cosine. Y behaves like sine. Z behaves like t. If you see cosine and sine, that is something circular, always. Like in engineering and physics, cosine and sine give you some circle motion. This is a t at the end. What do you think?
The cylinder?
Cylinder, interesting idea. Why do you think so?
I mean,
You can just say it's intuition, so you don't have to explain.
I mean, cosine of t and sine of t looks like a circle of some sort, and then t is linear, so
Up and down.
yes.
So it's a circle and it's keep going up and down. Interesting, yes?
Spiral.
Spiral. You also said spiral? Very interesting. More ideas? Very interesting, cool idea. You're right. So this is a circle, right? Well, I accidentally made a circle, but I just meant to say that this is a circle in 2D, right? If t is 0, then there's no third dimension. Remember, we just learned 2 weeks ago how to find intersections, how to flat something out in some dimension. Something crazy is happening, but with the moment z is 0, it's 2D now in x and y axis. If x is 0, it's going to go to y, z dimension. So if t is 0, it's just a circle, and we know how it looks like. It looks like this, centered at 0, radius 1. It's cosine and sine. So the t makes the circle not to be completed. When the circle is running, right, instead of completing here, t tells you, well, I want it to go higher or lower. So it's going higher or lower. In a 2D flattened projection, let's call projection, it's going to be still a circle. But if you want to watch from the side where t actually exists and t is height, at every different height, you will have a different circle. Check this out. So you both were right. It slowly describes a cylinder, but to be exact cylinder, it should have more variables there. This, because t is keep moving, it's keep moving up and down. I have a nice animation to show you this. You better start. Yes. Look at that. And again, remember, it's pointing at it. It's always pointing at it. See, from the center, it's tracing. It's called tracing. So spiral, how do you call that as well? A helix. Helix. I was keep calling it helix, and then someone fixed me. It was a helix. So, let me see. So, for you to know, helix, also that's exactly a representation of DNA. There are 2 helixes running around, DNA, right? And that's why mathematically all of those are sines and cosines all the time. So, interestingly, I'll show you. I have this tool, check it out. And then if I stretch it, it becomes a DNA spiral. See the shadow? Pretty cool. Let's see. Yeah, this is pretty cool. This is like a pointy massaging thing. When I read Ukrainian news, I sometimes have panic attacks. So this helps me to come down. Basically, once I accidentally noticed that this is DNA, exactly how cool is that? And this is a helix. It's a bit more complicated. When it's spiraling, it creates some triangles on the way. But it's pretty cool, so I decided to show you. You see it on the shadow. The shadow is a projection on 2D. So the shadow is just kind of like a heartbeat function, which is sine and cosine. It just goes up and down. But because it's repetitive, because it has a pattern and it has a cycle, that's sines and cosines. Whatever has patterns, those are sines and cosines. And that's why we're teaching you so much to learn about sines and cosines, which are super boring trigonometric functions, but they have so many applications. So if you ever want to work in applied science, which is chemistry, physics, computer science, you need to know tricks. That's the idea. So let me show you this. Highly recommend. This is a very fun thing to squeeze, to like not to let you have a full-blown panic attack. Now, here it is, a pretty cool idea. At any time, so what I'm showing here, if I fixed height at any moment, it just becomes a circle. See? Circle the height 1. X squared plus y squared. Let's remember, what does it mean to have x squared plus y squared? X squared plus y squared is cosine squared plus sine squared. That is 1. Well, x squared plus y squared equals 1 is a circle centered at 0, 0, radius 1. So now everything depends on t. If t is always keep growing or decaying, t is a variable. Always. So while the circle is spinning, the height is changing. So it grows up or down, right? Or down. So if you fix t and the third dimension, then it becomes the circle at some kind of level. But because t's keep changing in 3D, the circle is never completed. It's keep going up. So it's a broken circle. However, if you look at this cylinder shape from the top, what are you going to see? You will see a circle. It's a collection of circles. And that's why it's very interesting. As a three-dimensional creatures, we only see those 3D objects. But if you work in upper dimensions, we are the primitive creatures that only live in 3 dimensions. So if as a person who doesn't see 3D looks at the top and see lots of circles, but we see more dimensions into it. There's infinitely many not connected circles. So it's very interesting to see if there's a creature with upper dimensions, what do they see about us? And I will teach you how to find 4-dimensional objects creates a 3-dimensional shadow, how to find the volume of that shadow. So that's going to be pretty cool. So x squared plus y squared equals 1. That means that our curve lies in the cylinder. X squared plus y squared equals 1, just like you said, a cylinder. Z equals t means t is going up or down. So the curve is a helix, DNA, and also slinky. That's actually kind of a slinky idea here too. Pretty cool. Do you find that fascinating? So it's pretty cool that biology already has this idea from the moment we exist. Let's see if we have, if I want to do more or not. Let's keep this one. No, actually, let's do it. I will ask you, you don't have to write it down, but it's kind of fun to guess. Guess what's the difference with this one? Interesting. Can you guess? T cosine, T sine, and T. T is positive. Well, starting from 0. What do you think is that? Again, the hint I give you all the time. If you see sine and cosine, that's something repetitive, and it's makes some circle motions. Yes?
Like a tornado?
Tornado? Why would you think so?
Because the t is greater than 0, so it's only going up on the x, or it's only going one direction on the x, and then the t, there's also t's in front of the cosine and sine, the x and y, so those are also increasing. So it's just going to be going up.
Very clever. That is very clever. Did I interrupt you?
No, you're
Okay. Sorry, I got excited. So sine and cosine makes the circle motion. We multiplied each by t. That means the circles keep growing because the t's keep growing, right? So it will be 5 cosine, 5 sine. That means the cosine and the circle increased by 5. Then it's 6 and 7, and then 17.3, 2.1, and so on. Any real number, t's number, right? So the circles keep increasing, and the height is keep increasing. So the circles are getting bigger, and the height is going up. Check this out. Exactly. I was very impressed that you said the word tornado. It is a tornado-looking shape. If you look from the top, what you're going to see? This circle, this circle, this circle, and the biggest circle will be where like the biggest t you choose. If t is 100, that will be the biggest circle. The smallest circle is when t is 0, then it's 0, 0. So from the top, if you collapse everything in 2D, when z is 0, then it's just lots of circles. But from the side, we see a tornado. How cool is that? Like, this is the amazing idea. So the moment I multiplied my circles by t, I forced them to change the size all the time. So now this is like intuitively how you can work with those things. This is actually what 10.6, the one we're skipping. It's all about that. You can intuitively guess the shape of the curve. Calculus, write down calculus with vector functions. Yes, let's do calculus 1, but with vectors. Let's do it. So we don't have to write down lots of things here. whatever we learned in Calculus 1, do you remember the very first homework of Calculus 1 class? What was that? Limits, yes, your least favorite chapter ever. Everyone struggles with limits. It's very unusual to explain it. I always explain it using atomic bombs and explosions. So there's lots of some memes circulating in the internet. When I teach, I like explosions and black holes, like two things, my favorite things. So limits is something like there's an explosion happening over here, and I cannot be in the middle of it. So I'm making some chemical reaction, and when I add something, it explodes like atomic bomb. I want to know what is happening, but not getting killed. That's like the perfect situation. So I know the explosion happens when it's like over here. But I will step a little bit closer and there's still no explosion. So I'm adding more chemicals to the reaction. And I like a little bit closer and still no. So the idea of the limit is you can step as close as you want, literally as close as you want, to check out what is happening here, but you will never be at the moment of explosion, so you'll stay safe. That's the magic of limits. And also the infinity. We can check where the universe is going with emerging, and the planet's gonna die and the sun is gonna explode. How do we do it? We're not gonna live forever. That's limits. We're going to plus and minus infinities of time, which we call long run. What is happening with temp in the long run? You can calculate the growth of the population, the water problem, the renting problems. All of this can be calculated. So it's pretty interesting. We just define a function called a vector function, swallows the number and spits out the vector. Let's do all we learned in Calculus 1 with those functions. Limits, derivatives, integrals. So we're finally getting into interesting part. You don't have to write this down. Limits are limits. Basically, if you want to take the limit of, let me show you, maybe there's an easier formula. Example is easier. Maybe write down the first formula, but basically the idea is when you take a limit of the vector function, remember R is the vector function, you take a limit of the first input and the second input. Simple as that. So we're just going to practice. That's here homework. But that means you need to remember what limits are, and kind of do you? Because I don't plan to review that. It will take forever. But I have good videos in Calculus 1 class and everything, and functions, speeds of functions and everything. So let me give you one example and we're going to move on. But the idea is you take a limit of each component and you're happy to go. So that's why that homework is also have lots of examples, because they go fast. They go fast if you remember Calculus 1, which is like a kind of a question, you know. But if you don't post problems in the forum, we have several amazing people in the forum who I think checking the forum even when they sleep. And that's very impressive. And we should award those people with extra credit, I think, because they're always there.
We're CS majors, we never sleep.
That's a good answer. He says we are computer science majors, we never sleep. That's a good point. Yeah. So let's see. We already have several superheroes in the forum. So some people want to meet them, shake their hand, praise their work. Let's see. Let's do one example. R of t is ln 1 plus t, 1 over square root of 9 minus t squared, and 2 to the t. Find the limit at 0 of r of t. Let's see. Solution. Well, I know I'm going fast, but I will just slowly gonna write down. I'm looking for a limit r. So r is a vector function, right? R of t. T goes to 0. What is that going to be? Guess what? You plug t equals 0. Let's check first. What is the first answer? ln of 1 plus 0 is ln of 1. ln of 1 is 0. Good job. You were close. It's actually either or. It's usually one of these. When you plug t equals 0 into the second component, what's happening? So I'm plugging t here, here, and here. What's the second answer? 3 or 1/3. 9 square root of 9 is 3. And then the third one is 0. It's 1. Good job. 2 to the 0 is not 0. Some people freak out during the test and keep giving me those answers as zeros. Don't do that. So basically, this is what I did. Don't have to write it down. Did you guess? I just put limits everywhere. And I plugged whatever I wanted to be plugged, and you got the answer. Does that make sense? Remember, the answer is a vector. So at particular run, when t shrinks to 0, we get the particular vector, 0, 1/3, 1. But actually, the original function has infinitely many vectors there. And I just want to check, what kind of vector we have at 0? And 0 is a fourth dimension here, t. So we have 3 dimensions, x, y, and z. But then what is t? T is a 4th dimension. It's a parameter. So maybe temperature, maybe time. It's easier to imagine it's time. Interpretation, as t goes to 0, r gets closer to 0, 1/3, and 1. That is the idea here. We did that many times, calculus 1, so that should be good. Remember the continuity definition. R is continuous if, at A, if a limit, which is left limit and right limit, give you just a limit, right, of r of t, gives you also r of a. So there's no gaps and there's no holes. Here's the idea. No gaps, no holes. It's continuous. If there's a jump, not continuous. Or if there's a hole, not continuous. The intuitive way, if you put a pencil, can go through without taking the hand from the paper, that the function is continuous. But this is a strict definition. Limit exists and give you a finite answer, and at the point, there's also a finite answer, and they are the same. Integrals and derivatives, yeah. Remember we learned integration by parts, use substitution? Well, duh, we're going to go there in calculus 3. That was very predicted nightmare. We can take also integrals of the functions. You don't have to write this down, but you should understand examples. I guess that's just the example. Example, find integral of r of t if r is t squared, t cubed. You can write down integrals. Integrals. Well, guess what? You take the integral of each component. How bad is that? What is the integral of t? T squared over 2 plus c. Don't forget that. Then t squared gives you t cubed over 3 and t cubed t4 over 4. Each have some c. So either you write them down as c1, c2, c3, or abc, or whatever you like. Doesn't really matter. Just remember that those are constants. So you don't have to, again, that's the answer. Just make notes that if you want to integrate, you integrate component by component. Derivatives, most importantly, we can take derivatives of the function of the vector function, and that will have important interpretation. That will be very important till the end of the semester. So derivative actually gives us so much information. The derivative will be called a derivative function. Derivative of the vector function. Again, you don't have to write this down, but I'm reminding you that I give you all those notes. They are in modules, by the way. So the derivative was defined through the limit. Then it means all the properties will be maintained. If we just learn that limits work, then derivative will work too. So that's a proof why derivatives work, blah, blah, blah. Check it out. Derivative has lots of cool applications because we want to check the slope, how fast something is changing. That's derivative, right? How fast something is changing, instantaneous rate of change, slope, lots of applications. Now in 3D, 4D, 5D. So what is the slope at this moment? What is the slope of this moment? What is the slope of this moment? And not just the slope, but the direction. So if I have a paper bird, origami, right? Dropped in the floor, will it go up or will it go down? And how it will go? So that's the aerodynamics, how the planes are created. All of this have to be taken into account. The tornadoes, the swirling properties. I think I have some cool animation here. See, not only I'm still describing all of this, we are pointing, but in this case, the pointing one actually is a secant line. It becomes a tangent line, just like in calculus 1. And the other one is this one. Let's see. Wow, that's a very fast thing moving up. So all of these little arrows are tangent lines. Tangent line touches the spiral at some point, right? That is the idea. More? Okay, fine. Look at that. What if we have several movements? Which one is faster? Why? One vector is bigger than another. See, the magnitude of one vector is larger. The size. So that one goes faster because it's a force. So it's dragging that object faster, but slopes are the same. So we're gonna learn about that. And the last one is this one. Okay, the last one doesn't exist, so it's fine. Some of my amazing links disappear. Very upsetting. Let's practice. Finding second derivative. Okay, fine. Let's quickly find second derivative. Find r prime prime. If r is e to the t, e to the 2t, e to the 4t. That is just reminding you of chain rule, because I think you don't remember that. Solution. The first derivative will be e to the t gives you e to the t, e to the 2t, e to the 2t times the derivative of the function inside. Derivative of the 2t is 2. That's how chain rule works. I have very good videos on chain rule, because that's basically the hardest topic in Calculus 1 is chain rule. Same idea with e to the 4t. It's e to the 4t. You copy, then times, that's the wrong thing here, times 4, because it's derivative of the function 4t. That's the first derivative. And then the second derivative. Just repeat the process. That's going to be a vector. E to the t is still e to the t. Now 2e to the t becomes 4e to the t. And 4e to the 4t becomes 16e to the 4t. Exactly. Very good. Very good. That makes sense. Imagine integrating it back. Also, that is all possible. While you're writing it down, moving on. A new thing we can do with vectors function is to take a dot product and cross product together. So now we have two products. Remember we had product rule? Well, now we have two product rules. Dot product rule and cross product rule. Still works. The idea is still the same. It's just kind of annoying to do that. But yes, when I want to multiply, find r times s and r times s. One is a dot product called scalar product. Another is cross product called vector product, because the answer for the first one is a number, a scalar, and the answer for the second is a vector. Find that and then their derivatives, blah, blah, blah. And they are given. R is 1t, 2t, and s is t, 2t squared, 3t. I'll wait, don't worry. Well, that is not anything super crazy or new. We just need to find them. Today's quiz is literally about that, finding dot and cross products, right? So, for the first, I will not do cross product, it's too long. But r times s will be, so step 1, you actually find that, and we know how to do that. It's 1. Oh, let's review for the quiz right now. How convenient is that? What is a dot product? Dot product, you just multiply component by component and add the results, because the answer for the dot product have to be a number, not a vector. So the dot product gives me 1 times t, that's t, plus t times 2t squared, that's 2t cubed, plus 2t times 3t, that's 6t squared. That is supposed to be a number, but in this case it's a function, right? So it's a scalar function, because for any t, it gives you a scalar. Now guess what? We differentiate that. R times s prime gives you, t gives you 1, 2t cubed will give you 6t squared, and then 12t at the end. That is a derivative, and that's the answer they wanted. And you do exactly the same thing with a vector product, which is cross product. So you're going to be practicing that in your homework. And then guess what? Product rules. Now that we have 2. Product rule is the same. Do you remember product rule? I will write down the formula for you in general, and then you have nice notes. I teach it as u times v. U times v prime is, those are not vectors, it's just calculus 1, u times v. Derivative times copy plus copy times derivative. If you learn a different formula shape, doesn't matter, the formula is correct. We learned with F and G, blah, blah, blah. But that's the very short way to remember. Derivative, not derivative, plus not derivative, derivative. That's product rule. So now we have two product rules, dot product rule and cross product rule. And the idea is the same. It's just cross product rule is a heck complicated. But other than that, it's fine. Last two things to show, yes?
So in the dot product rule, the dots are just to do the dot product.
Yes, exactly. Very clever question. Those dots are the same as those dots. Cross are crosses. So see how careful you have to be now with all notation. Yeah, very clever. So the rule is the same, but now it's just applied to different stuff. Thank you for asking. And the most important, yeah, there was more questions? Yeah.
Why did you multiply T?
T. Oh, this one? Oh, that's not multiplying. Yeah, good question. That's a notation. R of T, right? And then S of T. So if they want to multiply first, they do like this. And then they're like, we probably should tell the reader what's the input. Is it theta? Is it angle? Is it time T? So they do T. So it's off. You can put in the pencil off. R times S of T. Yeah, smart. That's a very good question too. Notation, notations are all new sometimes. Thank you for asking. Okay, the most important is tangent vectors. That's important. And that's going to be two important things to show before we do the quiz. R prime of A is a tangent vector of R at A. R. So we will be asking you find the equation of a tangent line, but now in terms of vectors. And I will show you how to do it right now with steps. I always give nice steps so people can do it nicely. So here's the idea. Like in the animation I showed you, there's a curve. Here's a curve. I want to find the equation of a tangent line, and I want to find the direction of that thing. So it's increasing. So where? To the right, to the left, to the up. That will be called tangent vector, this red thing. Is tangent vector, direction or a slope vector. Now it's not a number anymore and not a function. It's a vector, direction slope vector on a tangent line. Direction or slope vector. That's R prime. R prime will be very important in even upper level classes. So find that. And this is what I'm going to show you right now. One more formula to write down, and we're going to do example. So sometimes they ask us to find R prime because it's a tangent vector. Tangent vector touches the function. Tangent, if you translate it, it's called a kiss. So it's kissing. It's like this one touch, while secant is cutting through. So tangent directional vector touches the function at this particular point and shows you where it's growing or decaying. Sometimes we don't need the size of that, like why this is like 5 units long. I don't like that. I just want to know the direction. So write down this important formula called unit tangent vector. That's going to go to the exam 1, final exam, anything. Your quiz, homework, unit tangent vector, unit normal vector, and it will be third one also, binormal vector. Tangent, unit tangent vector. I want to find R prime, but I don't want to have a size of R prime to be in calculations because I don't care. I want to know just a nice direction. That's it. So I divide by the size of R prime. That gives you tangent with the size 1. That's unit tangent. We just learned unit vectors, remember? So it's unit tangent. It's the same direction as R prime, but it gives you size 1. Because usually the size is on the way of calculations. We don't need that. We just need to know where everything is going. So the spiral, where does it go? All those tiny tangents, I don't want them to have different sizes. Let's practice to find both of these. Let me see if there's anything interesting to show. Oh, look at that. So we're going to learn tangent unit vector, normal unit vector, binormal unit vector. All of them will give us lots of cool information. So the red one is tangent unit vector. And then blue and green are normal and binormal. We're going to learn those next week. But today, let's practice this one. Let's see, what is that? Whoa, look at that. The moment we learn tangent vector, we're going to learn tangent plane. Of course, if the tangent can kiss the curve, then there's a plane that's kissing the curve too. So we're going to learn that and how the plane move around and cut each other through sometimes. So that's pretty cool too. Example, and we can start the quiz. Example. Find the equation of a tangent line. Told you. And the calculus 1, I told you that this problem, find the equation of a tangent line, will hunt you for 3 classes. Calculus 1, 2, and 3. We did it literally in every semester. Find the parametric equation of a tangent line to the following curve. T equals 1, and R is a vector 1 plus t, t squared, 3t plus t cubed. Following. While you're writing it down, I'll remind you, we're going to have a quiz today after this problem. And you should not leave the class early. I'll take points off if I see you're leaving early, unless you warn me and you have to be somewhere. Because the whole point is for your collaboration with others. Like last time I said, don't be smart ass and just like, I finished, I'm leaving. No, if you leave, I will relocate you to another room and you help people there. So that's the most important. I need to see that you're working. Originally, my quizzes were you submit them in class. So you have 10 minutes, your problem, submit them in class. So if I see people leaving too early, I will just switch back to submit it in class and you'll have to stay. But because it became more lenient, I started giving it take home. So you have 2 options. Either you stay until the end of class and help each other actively, and then you take it home. Or if you don't want to help each other, then I will have to submit in class. You choose. So, do you remember that to find the equation of the line, you need a point and direction? That's a new thing we just learned last time. To find the equation of a line, we need 2 things. A point and a direction. That gives you a line. Like so. Point and direction. Steps. If you see a phrase, equation of a tangent line, in any class, you start with derivative. It just kind of depends what kind of derivative it is. Calculus 1 derivative, calculus 3 derivative, matrices. But it always starts the same. You find the derivative because tangent is derivative. So at least you know how to start. We just learned how to do that. R prime, and it's a vector, right, of t is, I'm looking at the original R. 1 plus t gives you, bless you. 1 plus t gives you 1. T squared, 2t. 3t plus t cubed plus 3t squared. Amazing. Good job, people, remembering that. That's nice. Step 1. You see, you're already done with step 1. Step 2 is to plug. We need slope, right? Slope. Now it has different meaning, though. But the slope is whatever we find as derivative at all points. I need at one point plug t equals a, whatever is given. Sometimes you need to find it though. Sometimes you need to find it. In this case, they gave me t. What is it? 1. So r prime at a, in our case, r prime at 1. So the vector, specific time t becomes 1, 2, and 3 plus 3 is 6. That's a vector. That's literally first class of the semester. Vector we learn. 1, 2, 6. You know how to draw it. Oops, don't go. It's 1 towards me, 2 to the right, and 6 up. Nice, we got that. Put it in the box. We will need that. Put in information to the box because we will need it at the end. This is a directional vector. Direction vector. Remember, we need a point and direction vector to build the equation of a line. That's what we learned last time. We need a point and direction vector v. We called it v last time. That's a new information. If you don't remember this, it's fine. We just learned on Tuesday. Yeah.
So for a normal line, we would need a point and a slope, but for these kind of equations, we need a point and a direction vector.
So it's a good question. For all lines, we need a point and direction. But for normal line, because the direction can be found either as a slope or perpendicular one. You have two options in that case.
Yeah.
That's a bit confusing. That's why you feel like it's not clear. We're going to do more examples to clarify it at home in the quiz next week. But yes, all lines need a point and direction on it. And sometimes perpendicular to it also tells if it's perpendicular, oh, so it goes this way.
Yeah.
Yeah.
So the slope was the direction.
Yeah.
What we call the direction now, we use a vector.
Yes, exactly. Yeah, very good.
Okay. Thank you.
Question? Yeah, there was a question here. Okay. Let's keep going. So we have direction, now the point. Find, sometimes it's not given. Find the point if not given. Find the point. Why do I keep changing colors? If not given. The point is R original. Do you see it's original, not prime anymore? R at A. So we're plugging into original. This is exactly what we did in Calculus 1. You probably don't see it, A, because you're tired right now, and B, it was a long time ago. But it's the steps exactly the same as in Calculus 1. We also plugged the original point into original function. So I'm plugging into original R at 1. Okay, I'm gonna go and look at the original. R at 1. 1 plus 1 is 2. 1 squared is 1. And then 3 plus 1 is 4. That is going to be a point. 2, 1, and 4. So I'm plugging into original function to get a point. That's a point. Let me put it in blue. Point. Put it in the box, because this is what we need to build the answer. And the answer follows. Line, step 4. Step 4, equation of a line is point plus direction vector. That's ugly. Direction vector. So now we have both, and we know that formula. Write it down. R is R sub 0 plus V times T. Wow, nice. You just like died on me, seriously? So rude. Okay, one more time. You can write it down while I'm writing the next idea and compare. R is R sub 0 plus V times T. Nice. So put this in the box. That's the formula you need to know. It's an amazing formula. Very important. Basically, it's mx plus b, if you think about it. But b plus mx. Let me finish just a second. So we wrote it in two ways. R is equals either 214. Yeah, this is, I noticed a mistake, but I'll fix it in a second. 214 plus T2T4T. Or this way, 2 is the original one plus this 1 times T, right? Comma, that's a vector. Well, I'm thinking to write down which way. I think this way is better to write down than the formula they give us. Then 1, that's the original one, plus 2 times T, comma, plus 4, that's the original one, plus 6 times T, like so. This is the answer. See, the original point, 214, and then the slopes were used, 1, 2, 6. It's a slope for each case. So I used 214, color coding for you, and green, 1, 2, 6. Those are slopes. So that's repeating the previous material, but in a new way now, because now we had to find derivatives. Yes. Good. I found a mistake. Did you find a mistake? Somewhere? It's a small notation mistake. This is a point vector. Okay? So I need to change the notation like this, because this is R sub 0 basically. We call it R sub 0 in the formula. It's a point vector. It's a vector that points at the original point. Sometimes called original point vector. And this is the representation. Let me move it up. A curve called R at A. a line, that's a called equation of a tangent line, was built using a point. We found a point, and the point is 214, 214. This time I'm putting it in parentheses because it's a point, but there's also vector points at that point called r sub 0. And then the slopes are r primes. That's in red. Those are derivative vector, or in this case we call it direction vector because it points somewhere. Yes?
What was the original equation that we derived?
This one. This one?
Okay.
Yeah. To summarize, we had a curve. It looked like this. We asked to find equation of a line at t equals 1. So t equals minus infinity, minus 10, minus 0, 1, 2, plus infinity. At some moment of time, we were asking to find the slope. Here it is, this equation of a tangent line. So there's a line that touches the curve only at one point. To build a line, I need two things. A point, P, what the heck is that? And a directional vector, so something like that. And that's what we did. We found a directional vector first as derivative, plug t equals 1. And then we found a point, plug t equals 1 into original. And we built using the formula we learned before. Point plus v times t. V are slopes. Maybe let me remind you. Point, that's r sub 0, slopes. Slopes in the quotes because it's directional vector. V are slopes. T is multiplied by slopes. I have a joke at the end. There's a second. So you will have homework where you find this normal t, blah, blah, blah. That's not that hard. Okay, that's a question for you. Did you get any of this? Sometimes I feel like the lecture is hard. You know, like, did you get any of this? I feel like this joke can be put in almost every second lecture in this class. Right? You tell me. It feels like that. Good job, people. Good job for surviving, staying awake.